Hey everyone, Mr. Fransky here. Today we're going to be talking just about kind of the next step to the unit circle, which is the reciprocal functions. Those functions are tangent, cotangent, secant, and cosecant. And they're called reciprocal functions because just like you remember we had SOHCAHTOA, and then we had SHOHCHOCAHO. Remember, each of the secant, cosecant, and cotangent were all achieved by just taking reciprocals of sine and cosine, or tangent. So we're going to learn kind of a little bit about these. We're going to have a quick way to do it, and then also kind of a more theoretical way to do it, which is kind of the way I think about it. But let's kind of jump in. So first, let's talk about just some sine and cosine practice, just as bell work here. So remember, you have to figure out where this radian position is on the circle, and then sine, remember, is asking for the y, and cosine, remember, is asking for the x coordinate. So we want sine of 5 pi over 6. I always think about where that is on the circle. So 5 pi over 6, 1, 2, 3, 4, 5 is kind of the one that's right before pi over here. So there, sine is the short value, the short little vertical value. That's going to be 1/2. Positive because it's above the x-axis. Sine of 4 pi over 3. So when I see 4 pi over 3, I think of 8 pi over 6. 1, 2, 3, 4, 5, 6, 7. 8 is right down here. There's our 4 pi over 3. Sine there is the longer value, and it's below the x-axis, so it's negative root 3 over 2. I'm talking about the long and the short value. Remember, the order of sine and cosine is 0, 1/2. Root 2 over 2 is what happens at the pi over 4s. That's where they're the same. Then root 3 over 2, and then 1, right? That's the maximum we can have. Sine of negative 7 pi over 4. Negative, remember, is going to go down. So the pi over 4s, those are the x values. So I'm actually going to just write the x in there. So we have 1, 3, 5, 7. I started by going down because it's negative. So negative 7 pi over 4 is right there. Sine is therefore above the x-axis. That's going to be a positive root 2 over 2. Cosine of negative pi is the same as positive pi. We go positive pi or negative pi gets to the same spot. It's right there. Cosine of that value is the x-coordinate. It's negative 1. Lots of people make mistakes with that. They say it's 0. Sine there is 0, but cosine is negative 1. Cosine of 5 pi over 3, that's 10 pi over 6. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 is right there. Cosine is the short value there, right? Because sine would be the long. Short value there is 1/2. It's the x-coordinate, horizontal off of the y-axis there. Negative 5 pi over 6. Negative 5 pi over 6. 1, 2, 3, 4, 5. Remember, it's negative, so I start by going down instead of going up. So negative 5 pi over 6. Cosine there is going to be the long value, and it's on the left, so it's negative root 3 over 2. So I was remembering cosine is the x, sine is the y, short value, long value. As long as you have this little number line memorized, it's pretty nice, not too bad. All right. Take a look at the reciprocal functions. So here is the one-stop shop for the reciprocal functions. Definitely want to write this down in your notes. This is one way that you can just do reciprocal functions and not have to worry about anything else. So remember with sine, cosine, and tangent, we had SOHCAHTOA. So if you think about TOA, T-O-A, think about having a triangle. Got a theta right here. So if we have our opposite, our adjacent, and our hypotenuse. So sine, I guess we'll start with cosecant, sure. So sine is opposite over hypotenuse. Cosecant is the reciprocal of the sine function. So that's why SHOHCHOCAHO works. Whoops. SHOHCHOCAHO. Okay. So cosecant is adjacent over opposite. That's exactly the opposite of sine, right? Whoa, sorry. I'm mixing myself up. So this C is the cosecant, right? So cosecant is hypotenuse over opposite, which is exactly the opposite of sine. So it's a reciprocal. It's just 1 over the sine function because 1 over opposite over hypotenuse would give you hypotenuse over opposite. Right? So I call this the one-stop shop because if you know sine and cosine, this is all you need. Right? If you know sine and cosine, you just find tangent by doing sine over cosine. You do cotangent by doing cosine over sine, which is the same as the reciprocal of the tangent function, right? Because if you just flip this over, that would be the 1 over tangent. Secant is 1 over cosine, and cosecant is 1 over sine. So you can use this. The key to this is you have to know sine and cosine really well, right? So like, got some examples down at the bottom here. And let's just try them using these reciprocal functions. So tangent of 5 pi over 6 would be sine of 5 pi over 6 divided by cosine of 5 pi over 6. So 5 pi over 6 is just prior to pi. It's right over here. Sine there is short. It's 1/2. Cosine there is negative root 3 over 2. If you multiply by the reciprocal, that gives you a 1/2 times negative 2 over root 3. The 2's cancel. So we have negative 1 over root 3 to rationalize that and multiply by root 3 over root 3. You get root 3 on the top, and you get 3 on the bottom. Okay? So you can see there's a lot of work involved, right? But if you know sine and cosine, that's all you have to know. Next one's cotangent of root 3, or 3 pi over 2. So that's going to be cosine over sine. So cosine of 3 pi over 2 divided by sine of 3 pi over 2. Cosine 3 pi over 2 or sine of 3 pi over 2. 3 pi over 2 is the bottom of the circle right here. Cosine there is 0. And sine there is -1. 0 over -1 is 0. Cosecant of 5 pi over 3. Cosecant of 5 pi over 3 is, let's see, it would be 1 over sine of 5 pi over 3. 5 pi over 3, let's see, it's 10 pi over 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's right there, just past the bottom of the circle. So the sine there is -√3 over 2. So this is 1 over -√3 over 2. Multiplied by the reciprocal, that is 2 over √3, and it's negative. And multiply by √3 over √3, we get -2 √3 over 3. So again, a lot of work on the fractions, a lot of work with the rationalization, but that works just fine. Secant of pi is 1 over cosine of pi. Cosine of pi, pi is on the left side, that's -1. So this is 1 over -1, which is just -1. Okay. So if you know this one-stop shop, really, you're good. But sometimes you get into a little bit of trouble. For example, if you wanted to have like tan of, let's say tan of pi over 2. That'd be sine of pi over 2 over cosine of pi over 2. Pi over 2 is the top of the circle. Sine there is 1, cosine is 0. That is undefined. So we actually do have some points on these that are undefined. Why is it undefined? Because it has a 0 on the bottom. So some of these are going to be answers that are undefined, which is fine. Now, the one-stop shop is great if these three things are true. If you're really good with fractions, right? Multiplying by reciprocals, canceling greatest common factors. You might have noticed that on some of these, right? I don't know if we had to cancel the common factors. Yeah, we had to cancel the 2's here. We had to rationalize with that √3 over √3. Over here, we had to multiply by a reciprocal as well. So that's one thing, is you have to just be really solid with your fractions. You also have to be really good at rationalizing denominators, because you can't leave something like this. You cannot leave a root in the bottom. You would have to multiply by √3 over √3 to do that. So that's the second piece, is you have to be really good at rationalizing denominators. You also have to know sine and cosine inside and out, right? Because if you're going to do 1 over sine, or 1 over cosine, or sine over cosine, you have to know those functions to start with. If you don't know those functions, you're hosed, right? So these are some unacceptable answers. You cannot leave things like this. You can't do like 1 over √3 over 2. That'd be like a secant or a cosecant answer, right? 2 √2 over 2, no good. You got to cancel out those 2's and leave it just as a √2. 2 over √3, no good. That'd be like this, just simplified, right? Multiply by the reciprocal. Also can't leave, this would be like a tangent or a cotangent situation, right? Where you have √3 over 2 over 1/2. Cannot leave them like that. You must simplify. This one simplifies to 2 √3 over 3. This one simplifies to √2. This is also a 2 √3 over 3 if you multiply by √3 over √3. This guy would simplify to just √3 because you multiply by the reciprocal and the 2's cancel, right? So you have to have those algebra skills that fast. You just have to be able to look at it and say, oh, I can do that. It's 2 √3 over 3. If you get used to it doing it this way, you can get pretty fast, but I don't love this way. It's not my favorite. So let's talk how I kind of think about this. I get tired of rationalizing denominators. You have to do it all the time. It's no fun. So here's where these functions actually come from and how I think about it. So the one-stop shop is fine. If you want to do it that way, that's just fine. But let's actually talk about what these things are. So what is a tangent or a cotangent? And what is a secant or a cosecant? What are these lines? So on a function, we talk about this in calculus a lot. A tangent line, we've actually talked about this a little in pre-calc too, but a tangent line is a line that just kind of bounces off of a function. So it's a straight line that just kind of bounces off of a function. So that'd be a tangent line right there. You could put a tangent line over here. Okay, so a tangent line like just scrapes past the function. It touches at a single point and it just kind of bounces right back off. That's what a tangent line is. A secant line is a line that goes through a function. So it touches it at 2 points, kind of like that. It's a secant line. So when we're talking about our circle, there are very specific tangent and secant lines we're going to talk about. The tangent line is the one that's going to be, it's going to touch right at our 0, like where we start for standard position counting angles. That is what's called the tangent line. And then for the cotangent, maybe I use a different color, maybe red. Okay, so the cotangent line is the one that is, if I can make a straight line, is the one that touches the circle right at the top. Okay, so that guy right there is the cotangent line. Okay, so cotangent touches the top, tangent touches on the right side. And we're also going to kind of cheat. We're going to use the bottom line as well for cotangent. Okay, and then for blue, we could use one on the left as well. You can actually just use the one, but it's a little bit easier to think about if you use it that way. And then the secant lines, I'm going to use blue because tangent and secant are often kind of thought about together. So secant lines are ones that go through the center of the circle and cut straight across it. Okay, so that guy right there would be a secant line. And then our cosecant line. Cosecant line is actually the same thing, but it's going to kind of connect to the red one. So cosecant line, maybe I'll make it like this. But it just has to go through the middle. And then it's going to connect to the red. So really we care about the red connections where the cotangent and the cosecant line connect. And then for the blue, we care about where that blue line connects with the blue line right there. We're going to kind of talk about what these things mean and how we figure this out. But I just want to show you where these words come from, right? Tangent is just kind of bounces off the function. Secant goes through at 2 points. Okay, so secant line goes through the circle. Tangent line just kind of bounces off. It just touches and bounces off. So why is tangent sine over cosine, and why is cotangent cosine over sine? So let's kind of think about this. I'm going to draw in our tangent line right there. The way that tangent is defined, if you're at a certain angle, so let's say we're at an angle, something like this, so there's our theta, okay? This length right here is defined as tangent of theta, right? And we know from what we talked about in the last lesson that if we draw in these values, right, that length right there, that would be the y-coordinate of that point on the circle. That right there is sine of theta. And if we use a different color, maybe green, down here, that length right there is cosine of theta, right? Because that would be the x-coordinate of this point right here. That would be cosine theta, comma, purple, sine theta. Okay? That would be the coordinates of that point right there. Tangent is if you keep extending that line out until you hit that tangent line. That length right there is tangent. So why is tangent sine over cosine? Well, what we've created here are similar triangles. So be careful with my colors here. If we think of our big triangle, well, let's use the little triangle first. So we have the little triangle has that little guy right there, and then we have purple coming down, and we have green on the bottom. Okay, so here's cosine. Try to stay in my color palette here. This is sine, and then right there we have theta. Do that in blue. And then our big triangle, just do it all in blue. So this guy is still theta. This guy over here is tangent theta. What's this length down here? Well, this is the unit circle. What are the coordinates of this point? It's 1, 0, right? So that length on the bottom is 1. So these are similar triangles. You may have learned about similar triangles back in geometry. I sure hope you did. And in similar triangles, you can do ratio of side lengths are the same. So over here we have tangent theta over 1, which is just tangent theta, is equal to, well, the tan is the same as the sine, and the 1 is the same as the cosine. So this is where tan theta equals sine over cosine comes from. Okay? So I just wanted to show that to you. That's where the one-stop shop comes from. It really comes from the geometry of the circle, which is kind of cool. So let's talk about the values. Let's actually figure out what these values are going to be. So as you're going up the side of the circle, we have our pi over 6, then we have our pi over 4, then we have our pi over 3. Okay? So here we have our pi over 6. This would be tan of pi over 6. This would be tan of pi over 4. This would be tan of pi over 3. So as we talked about before, as you're going up the circle here, what's happening to the tangent value? It's getting longer and longer and longer, right? So tangent of pi over 6, tangent of pi over 4, tangent of pi over 3, it's getting longer as you go up. So we're once again going to kind of create a little number line for this, right? For sine and cosine, it was 0, 1/2, root 2 over 2, root 3 over 2, and then 1. Tangent has a different number line, okay? And I think it's worth memorizing. So what's going on here is as we go up, we're getting bigger. And really, we can think about this in terms of like kind of special triangles. So this first one is a 30, 60, 90 triangle, right? 60 up there and 90 down here. You can also think about it in terms of a sine over cosine. So sine of pi over 6 divided by cosine of pi over 6. You can also think about a similar triangle. Remember the 30, 60, 90 is the 1, 2, root 3 triangle. So what you have to do is divide everything by root 3 to force this to be a 1. So if you divide everything by root 3, divide by root 3. Oops, that's a bad 3. Okay, so the root 3 over root 3 on the bottom becomes a 1. 1 over root 3, which is exactly what we're going to get here, because sine is 1/2. On the bottom, we have cosine, which is root 3 over 2. Multiply by the reciprocal, you get 1 over root 3. right? So either way you think about it, you get 1 over root 3, but we have to rationalize that. Multiply by root 3 over root 3 gives us root 3 on the top, and the bottom root 3 times root 3 is 3. Okay, so root 3 over root 3 is actually the second value, because if you do tangent of 0, think about the length of this line if we squeeze it all the way down to 0. If you squeeze it down to 0, there's nothing there. So the smallest value of tangent is 0. So tangent of 0 is just 0. Next is tangent of pi over 4. This is a 45-degree angle. So if this is 1, this guy right here must also be 1. You can also think about it in terms of sine and cosine. Root 2 over 2 divided by root 2 over 2, they're the same thing. So it's just 1. So tangent of pi over 4 is 1. Tan pi over 6, root 3 over 3, tangent of pi over 4 is 1. Tangent of pi over 3, this is now just a big 30, 60, 90 triangle. And because the bottom is 1, because this guy is 1 down here, this length should be just root 3. But we can do sine over cosine. So sine of pi over 3 divided by cosine of pi over 3 is going to be root 3 over 2 divided by 1/2. Multiply by the reciprocal, the 2's cancel, and you just end up with root 3. So root 3 is our next value. Now how about the last one? At pi over 2, what's going to happen with these lines? When is this line going to intersect this one? Never. That's why tangent of pi over 2 is undefined. Okay? And then we can use these values just to come back down the other side. So here, if we think about our tangent line over here, you could also think about it kind of going down this way and intersecting over here, but it's just going to come back down, right? We're going to have a root 3, then we're going to have a 1, and then we're going to have a root 3 over 3. But the difference is if you think about sine and cosine over here, or you think even about how this is going down on this line, over here sine is still positive, but cosine is negative. So these are all going to be negative values. And then back to 0. Then down here in the third quadrant, it's going to, if you came out to this side, it would be positive. And it's the same if you think about going to this side, because the sine and cosine are both negative over here. So here we're going to have positive values. We're going to have positive root 3 over 3. Oops. And then positive 1, and then positive root 3. Down here, we're undefined again. In the fourth quadrant, we have positive cosine values, negative sine, so we're going to have negative root 3. And then we're going to have negative 1 and negative root 3 over 3. And those are all the values for tangent. I think it's way easier than sine and cosine, right? You just think, is it the short, medium, or long value? Root 3 over 3, 1, or root 3. And then we have 0 at 0 and pi. And at pi over 2 and 3 pi over 2, we have that undefined point. All right, so let's talk about cotangent. Cotangent just uses this line instead, here and here. So let's think about it. If you start at pi over 6, the cotangent value is going to be this guy right here, cotangent of theta. And here's theta down here. And then it's going to get shorter as we go. But the values should be the same as tangent, right? We're going to start at root 3, then we're going to have a 1, then we're going to have a root 3 over 3. So the number line is exactly the same as tangent. It's just, if you want to think about it going backwards, we'd be undefined at 0, and then it's getting shorter as we go. So then we would have on the left side, the positives and negatives will be the same again. So here we would have negative root 3 over 3, then we'd have negative 1, then we'd have negative root 3. Yeah. And then undefined here, coming around. Down here we would have positive root 3 because now both sine and cosine are negative. Then we'd have positive 1, then positive root 3 over 3. Over here we would have, let's see, it'd be negative root 3 over 3, then negative 1, and then negative root 3, and then back to undefined all the way around. So positive, negative as we go around. Same values. So we go 0 at the top and bottom. It'd be 0. Maybe write it backwards since it's the opposite of tangent, right? So we'd have undefined, and then we're getting shorter as we come along here. So we'd have root 3, then 1, then root 3 over 3, and then 0 at the top and bottom, because that's where the line touches. Oh. All right, so secant and cosecant use the same triangles. So for secant, got a line here. There's our tangent line. When we extend, so we said this value right here is tangent. This guy right here is going to be our secant value. Okay, so as we go around, as we go up here, secant's going to be getting longer and longer and longer. And at the top, it'll be undefined again. We'll get to the values on the next slide. Then on the left here, it's going to come from big back down. Then we'll get big again. And then we'll be undefined at the bottom again because it'll never touch. And then over here, we'll get small. So it's the length of the hypotenuse of the same triangle. Cotangent, I used red before, so I'll do that. or cosecant, excuse me. We use those cosecant lines. It's going to be the length of the hypotenuse right here. So they're going to use the same, sorry, we're going to use the same number line for both. It's going to be kind of like the other one, where it's going to kind of do the opposite of what the other side did. So yeah, just like tangent and cotangent, how they kind of were the opposite, it's going to happen with the same thing with these two. So as the secant is increasing, the cosecant will come down and decrease here, and it'll be undefined, same places as cotangent, so undefined here and here. Okay. So let's think about the values. So let's think about those same triangles we had before. So if we have kind of a triangle like this, and then like this, and then like this. So that first triangle, we said this was a 1. We said this was a root 3 over 3, right? Because that's our tangent value. So to find that last value, let's just use Pythagorean theorem. So if we do 1 squared plus root 3 over 3 squared, which is going to be 3/9, it's 1/3, is going to be equal to our secant value there squared. So let's call it x. So we have 1 plus 1/3 equals x squared. So that's 4/3 equals x squared. So we take the square root, we get 2 over root 3, which is the opposite of root 3 over 2, right? It's the reciprocal of root 3 over 2. That makes sense for the kind of the secant values, because it's 1 over cosine. So then we rationalize that, root 3 over root 3, we get 2 root 3 over 3. So that is our secant value for that first guy. I'll just write that in there, 2 root 3 over 3. The next one right here, so this is a 1, 1, root 2 triangle, so that's just a root 2 there. Yep, so this is root 2, because this value for tangent is 1, so it's 1, 1, root 2. You can do that with Pythagorean theorem as well. Then the last one up here, we said this was a 1, this was a root 3 for tangent. This is a 2 then, so it's a 2 value. Then at the top, it's undefined. Now, the other weird thing is when you squeeze it down, tangent here we said is 0, but think about the length of this secant line as we kind of squish it down. What's the shortest it's ever going to be? Shortest it's ever going to be is 1. So we have here, so we go 1, 2 root 3 over 3. That's the most commonly missed one, just because it's a weird number. Then we have root 2, then 2, and then undefined. Okay. All right, so that is our number line for secant and also for cosecant. Cosecant is just going to kind of go backwards. So cosecant would go, let's grab a red here. So cosecant would go undefined, right, because we're kind of thinking about this guy right here. And the next one would be the longest possible one. So that would be a 2. Then it would be here. Notice it's the same spot, right? Same spot for both secant and cosecant. That's going to be a root 2. Then here we have a 2 root 3 over 3. And then we'd have a 1 over here, right? So it's just going to go backwards for cotangent. Or not cotangent, cosecant, sorry. So cosecant is just going to go backwards. All right. So last question is going to be positive or negative. Let's go back to our standard color for this guy. So for tangent and cotangent, these are the same. Because remember, tangent is sine over cosine. Cotangent is cosine over sine. So it's just going to depend on if sine and cosine are positive or negative here. In first quadrant, they're both positive, so it's going to be positive there. Second quadrant, we have positive sine, but we have negative cosine, so it's going to be a negative. Third quadrant, they're both negative, so we're going to have a positive there. Fourth quadrant, we're going to have a positive cosine and a negative sine, so it'll be negative there. For secant, remember secant is 1 over cosine, so it's going to be positive wherever cosine is positive. That's on the right side, because we have positive x values over here. On the left side, we have negative x values, so it'll be negative and negative. For cosecant is going to be positive when sine is positive, so that's the top, because it's 1 over sine. And then it's going to be negative on the bottom, because that's when sine is negative. So let's try some practice problems and get out of here. So tangent of 7 pi over 6. Could do the one-stop shop. I'm going to do all of this kind of using the circle, kind of thinking through this, how I want to do it. So 7 pi over 6 is just past pi. Oop, my pen cooperates right there. So that's going to be the shortest possible value for tangent, and it's going to be positive because both sine and cosine are negative there. So it'll be positive root 3 over 3. Trust me, you will get this fast at this. It's not that bad. Secant of 5 pi over 3. 5 pi over 3 is 10 pi over 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right there. So if I think about secant, it's going to intersect the normal tangent line. It's going to be the longest possible value for secant. And secant is 1 over cosine. We're on the right side, so it's going to be a positive 2. right? Thinking about our number lines, there might be a good idea to have those here. So for tangent and cotangent, it goes 0, root 3 over 3, and then 1, then root 3, and then undefined. That's for tangent and cotangent. And then for secant and cosecant, secant and cosecant, we go 1, and then 2 root 3 over 3. Then we have root 2, and then 2, and then undefined. Notice all those values are bigger than 1, because if you think about the reciprocal, when you divide by a number smaller than 1, like sine and cosine, you'll always get a number bigger than 1. So that's our secant, cosecant. So that was the longest possible value for secant, so that's 2. Cosecant of 2 pi over 3, that's 4 pi over 6. 1, 2, 3, 4, it's right here. Cosecant there, so we think about our cotangent line. That's going to be the smallest possible value. Cosecant is 1 over sine. We're on the top, so it'll be a positive 2 root 3 over 3. Because it's the shortest value without being 1. Cotangent of pi. Pi is over here. Cotangent line's there. Those are parallel lines. It's undefined. Tangent of negative 5 pi over 4. Negative 5 pi over 4. 1, 3, 5. That's right there. Tangent line there. So it's going to be some kind of a 1, and we're on a spot where sine will be positive, cosine will be negative. It's a negative there, so it's going to be a negative 1. Boxing all my answers, apparently. Cosecant of negative pi over 4. Negative pi over 4 is right there. And cosecant there, so we think about the cotangent line. Doesn't really matter because it's a pi over 4. It should be the same. So there, cosecant is 1 over sine. We're on the bottom, so it'll be negative root 2. All those 45s give us the root 2s. That's kind of the middle value. Secant of negative 3 pi over 2. Negative 3 pi over 2 brings us 3/4 of the way around backwards. That's up here. Secant there, parallel lines, undefined. Cotangent of negative 11 pi over 6. Negative 11 pi over 6 will be backwards almost all the way around. It'll be right there. Cotangent uses this line. That's going to be the longest possible value of cotangent, which is a root 3. All right, so a little bit of practice. Do the yellow sheet that you got, and a little bit of practice with this. Eventually, hopefully, you'll be able to improve your speed a little bit. When we do unit circle quizzes, I won't test you for speed, but I will test you for accuracy, so it's important that you can study these and get used to kind of these values. I love you guys. That's why I'm here. Have a great day.